How's it going, everyone? Euler Gonzalez here again, looking at the advanced Redux, specifically of what is Create Reducer. What is this Create Reducer is doing behind the scenes, which is, as we discussed in previous videos, is that, well, this is a function that allows us to make the state update logic maintainable, aka it's just a function that takes an state and an actions to generate a new bit of action. And because of that, you have a particular way to do that. This is also because it follows this flux architecture. This is the way of how you can create now modern web client-side applications that provide the best user experience for the customers, the clients, and even yourself. So the whole point of that is to understand now what this function is doing, especially what is the problem that Redux actually solve. Because if you use Redux foot, you have to actually create all of these different files that allow you to create now a reducer, or aka a particular architecture that allows you to make those state updates predictable. So that's why the Flux architecture is followed. So you have now the action, the dispatcher, and the state, and then it's going to be reflected across all of the UI components that is using that. Great, so far so good. So the idea is that because that requires a lot of ceremony. So when you create your reducer function, you also need to create first your actions that is going to be indicating it like, hey, all of the different objects follow with this particular format type that indicates the type of actions followed by the payload. What is this actions going to pass to the state, and you have a particular file to define all of your types in a constant file, and then all of your objects, actions objects, and then you have another file to define is the dispatcher logic, or the reducer, or in other words is like what you want to do when this actions has been dispatched. So once this a user or a input, whether it is computer or human inputs, in computer input is like fetching data, loading image on the browser, for example, or in humans you have typing, scrolling. So depend of the type of inputs, you want to have a particularly predictable way of how those states change. So this is the Flux architecture, and because require all of the things that you have to do per hand, now Redux say it's going to now simplify all of this ceremony for us by allowing you to create with a function all of the things behind the scenes. So we look at the create slide, which it now takes an initial state and a reducer, as well as the name slides to generate now actions, type actions, reducers, and the state proper to that slide. So why this is important is to, when we have now our first, when we're gonna actually code this on Visual Studio Code right now, we're going to see that RTKey, this advanced Redux, actually help us to automate that particular process, that ceremony, and also provides better TypeScript support, because when you have to use all of those things on foot, you also need to rely on some arcane TypeScript as a way to make everything work as expected. And the another thing is that when you need to actually add some middlewares to this reducer, or to the Redux, because one of the great things of Redux is that it allows you to now make the state management debuggable, so you can also see that using time traveling. But when you want to extend the functionality there, so for example, you want us to now handle more data models, it sometimes can become quite you have to Google a lot. All right, so the idea is that they're also going to make that integration or adding this middleware in a breeze, as well as handling is this side effects or data fetching specifically. So that's quite interesting, because knowing and exploring and describing all of this kind of thing, finally lead us to what we really care about, which is the create reducer, right? And what is the problem that, for example, first, what is the problem that create slide solve, something that I mentioned before, as well as what is the problem that create action solve, which is now give us the function. So we have now these functions that we're going to generate is type object action for that. So you have the type followed by the payload, as well as provide some types out of the box, which is a great thing. And also the reducers. So in the case of reducers, because as we mentioned, as I discussed earlier, the reducer is just a function that takes an initial state or an state and an actions to generate a new bit of a state. The idea here is that Redux recognize that sometimes you can this can be error prone if you're not careful of what are the case that you want to cover. One. Second, is also not TypeScript friendly, so you have to actually do that on yourself. And last but not least is that when you're going to update the state, things started to be very interesting here, because you're not going to mutate the state. You are going is to generate a new bit of a state. All right. So when you want to actually update, let's say, a small object with one, you want to update one property at one level object, and in there, if you want to update one single property, that thing is easy to do, right? But if you want to actually update 2 or 3 properties in a nested object, 2, 3, 4 levels, you have to now per level clone that object, copy that object. You can use a spread operator per level. So this can become quite hard to read, and not to mention that is now they introduce some particular problems, which is since we are now generating is a new state, which is a great thing because it makes our life much more easy when it comes to actually detect and to know the state change about that data, right? The problem is that we're going to generate is we have limited CPU and RAM, right? So anytime you do that, anytime you create a new state, you not only use CPU but also memory. And every time you do that, you're going to do that again over and over and over and over. That's not quite efficient, by the way. And the promise of immutability, which is something that it can be quite confusing, especially if you come from a natural human language. Okay, immutability means that things that won't change. It's like forever. So the idea is that in the context of computer science, okay, immutability means something quite different. Immutability means is that we need to have the ability to track state change in an object. that's the whole premise here, and this is something that Hale Simpson actually mentioned, and I really love that he described that, my friend. Oh yeah, it is, bro. Oh yeah, it is. Yeah, immutability. Okay. And you may wonder why this is important. Okay, so what is the problem? Yeah, what is the problem? No, you.
Let's come back to that concept of immutability that has come up several times today, where we said that immutability and immutable data really go hand in hand with functional programming. And we saw that changing things, especially changing things out in the world, feels not functional, feels pretty side effecty, feels pretty not pure. So let's take a look at how we can think of
from the master, yeah. But I want to look at from Kyle Simpson. Exactly. So which is something that Kyle Simpson mentioned.
If you choose to reassign it to a different value later, which is what's happening on line 6, no problem, of course, everything works fine. But if you try to reassign something that is declared as a const, you get an error saying that's not allowed. It's not allowed for you to change or to reassign. As a matter of fact, we really need to get into the word change, because the word change implies that we're changing something about the value itself, and we're not really changing the value. Base price is not being, its value is not being changed, its value is being reassigned. Immutability is important, but then what kind of immutability are we talking about? So immutability is the idea, obviously the word implies that something isn't going to change, but that doesn't fully encompass what we're talking about. It's not just that things don't change, it's that things don't change unexpectedly. There is obviously in our programs a lot of state change. That is the whole point of our programs, is for state to change over time. And state change being the point, you don't want to stop that from happening. There's really no such thing as like making an immutable program, because that program wouldn't have any point. There'd be no reason for that program to exist if nothing could change. So really this idea of immutability it's broken in our brains, or it's miswired in our brains when we think about it in terms of things that can't change. That's not really the point. Really the point of immutability is that change that needs to occur needs to be intentional. It shouldn't be accidental. It shouldn't be happening without us being aware, happening at different times, creating race conditions, all those sorts of things. Thing could change. So from happening, there's really no such thing as like making an immutable program, because that program wouldn't have any point. There'd be no reason for that program to exist if nothing could change. So really this idea of immutability it's broken in our brains, or it's miswired in our brains when we think about it in terms of things that can't change. That's not really the point. Really the point of immutability is that change that needs to occur needs to be intentional.
So that's what we're gonna do. So today we're going to talk about immutability, and I think that we're going to hit the break, so then we can move on to the next one as a way to understand one of the tools that, for example, Create Redux is using behind the scenes. What is the problem they're actually solving, right? So you have now Immer, which is this convenient way of how you can now generate a new state in a mutable syntax, JavaScript like, right? But behind the scenes, what it's doing is generating is a new state by using is a proxy, which is building all JavaScript objects. That what it does is to wrap the object and intersect any of the JavaScript built-in methods. So for example, get, set has some property, enumerable, as well as other internal method that object has, right? So anytime you update the state, that proxy detect that change and act upon that, act accordingly. Similar to set, as well as other properties. So, but yeah, in today's video, we're gonna talk about that, my friend, right? So what's the problem that Immer solves? Is like, yeah, muting internal data sometimes leads to problems. And all developers know, software developers know that if something is working, you don't touch that. especially if you're working on, for example, huge, gigantic applications like Java, where there is a lot of moving pieces out there, and if you change something, they might be rippling effect across your entire applications. So something that you don't want to do that. But the idea here is recognize that particular problem, especially when you need to change the state of application, because eventually you need to change the state of applications. Otherwise, that program will just not be helpful. All right. It's just only one single program that do one thing and only that, and doesn't have the capability to adapt or things like that. It's like, yeah, it's pretty useless.
Determined for that program to exist if nothing could change.
Exactly. It's pretty useless in terms of if a program can change its state, which is something interesting. If a program can change its state, that could also lead to ourselves. But in the context of programming, if you or a program can change its state, can change the way it processes data or do some things. So, for example, add two numbers, subtract, multiply, divide. If it cannot do that, what happened is that what is the utility of this? Okay. I think there is no reason for a program that exists if nothing could change. So there is no usability, there is no utility on a program stateless that cannot change. That's the whole promise of this, right? So because of that, programs need to change is a state as a way to update that. And when you mutate that object, so for example, you want to see your balance account. If that data doesn't change, let's say you have $100, and if you, for example, deposit $50 to your mom, and then your employee paid you 1,000, and that data still reflect 100. You get the idea. So with a single example of the balance accounts, okay, because we want to mutate the state of that application, mutating the state of these applications can lead to problems, especially if there is a lot of people contributing in these large code bases, because change that you introduce to change that you introduce to the code base can lead to some rippling effects, especially if you're building large web applications. So because we don't have the ability to knowing what's going on so far, especially when you change the state of application, you need to do that on foot, and that's a very cognitive load. So Eimer says, it's okay, let's go to solve this problem by, instead of actually mutating the object itself, let's go now to create is this immutable data structure. But the question is that what is immutability? Immutability, because we need to understand this particular problem. Okay, so what is immutability? So in the context of software engineering, immutability means, so in the context of software engineering, immutability means immutability doesn't mean that a program state won't change, because otherwise I think it wouldn't exist. But there is no need for that to exist. It wouldn't exist. Because otherwise, I think it wouldn't exist. There is no reason or utility for that. So, immutability here immutability here. So immutability here is the ability, okay, because this is an adjective, okay. So it's the ability.
So really this idea of immutability it's broken in our brains, or it's miswired in our brains when we think about it in terms of things that can't change. That's not really the point. Really the point of immutability is that...
Exactly. So immutability here is the ability. So the immutability here is the ability that change occur intentionally, or with intent. A change needs to occur with intent. Is it? So immutability here is the ability that change needs to occur with intent.
Change that needs to occur needs to be intentional.
Okay, it's the ability to change, that change need to occur. Exactly, it's the ability that change, that needed change. I think it's this. So immutability here is the ability that needed change needs to occur. Needed change needs to occur with intent. That's the whole point of this. So immutability here is the ability that needed change need to occur with intent. That's what happened. So
it shouldn't be accidental. It shouldn't be happening without us being aware.
Exactly. So it shouldn't. Yeah, it shouldn't be. It shouldn't be accidental, happening outside of our aware. Here we're talking about control.
Happening at different times, creating race conditions, all those sorts of things.
Happening at different time, creating race conditions.
So immutability is this concept of how do we control mutation? How do we...
It's like, how do we control mutations in an object? How do we control
change?
How do we control change? Oh. Oh my God. That's one of the, there is a reason why software engineer has proven to be more practical for investors as a way to now try to control the real life, to control the material life, the material world for our benefits, which is something that is inevitable. But when it comes to trying to control other human beings, or it is funny because most of the time those changes we try to control are outside of us. So something that is outside of that. But if we started to control our inner state or inner change, things will be not only quite different, but also more aligned to nature, more aligned to what truly is, what truly nature wants from us, or we align to our nature. So again, this is just a thought of myself, and that's one of the reasons why we should is, again, this is something that this is something that I do for myself, which is, well, recognize that it is better for you to actually focus on the thing that you can control as it is, right? And by that it means that, well, you need to actually have a very honest and open discussion with yourself, with your inner state. That's why if you truly want to provide value, if you truly want to change the world, right, you need to start with yourself. Yeah, and this is something that can be quite obnoxious if you say it out loud. Mainly because, yeah, we know that, right? It's like, but few actually act accordingly. So this concept from immutability, which is the way of how you can now control is change, or how we can control is mutations, okay? It's something quite interesting, and most of us, and I get it, why a lot of, as we continue to move on as a humanity, right? When we started to explore other areas, we started to having better problems. So instead of worrying about what we're gonna eat today, if we have water or light or the gas, which is the basis of Maslow pyramid, and everybody can speak that out loud. It's like yeah, but they barely feel that or pass through that, and then you started to have more and more better problems, all right, as you go up into the Maslow pyramid of needs, which is security, and then you have now other things that I don't remember until you realize, until you enter the self-realization. So the idea of this is to, when the better problems we're starting to face, all right, the more we will need to actually look inwards as a way to solve the external problems. That's perhaps one of the most counterintuitive things, especially in today's world. And that's also a reason why am I here, because with this extensive experience that I have right now, well, I just only have 34 years. I learned that from the hard way that you like it or not, if you are not able to, as on the US, I love to say, if you're not able to put your trash together, do not say the other word. First, no one cares about that. One. Second, you are not going to be able to feel yourself good. And emotions are something crucial in your life. Emotions is what the logic is moved by the emotions. So logic or emotions move the logic. So emotions serve the logic, right? And I think there's a lot of people, because they want to have control, because they want to now play in these political games and that kind of things. Emotion is something that is very, very, very powerful. And these inner forces, for example, like Carl Jung and other psychoanalysts discuss, is that those inner forces that is in us, this dark side that living within us, we need to make them aware. We need to actually bring that to the table, all right? Have a conversation with them, because if we're not, suddenly it appears, and we will actually do something that we actually don't want. Yeah. Oh my God. That's why we have. That's why we have, for example, in in U.S. society, okay, highest peak of violence in terms of mass shooting, it becomes a national sport. And to me, it's like, what? Oh my God, it is for real. I mean, this is just part of these expressions that live inside of us, and when we are not able to face that and to talk about that, a lot of hippie tends to travel to Peru and then take ayahuasca to find themselves, and then all of these shamans say, "What the f are you doing here?" It's like, what the f are you doing here? You should come back to your what the f are you doing here? You should come back to where you come from, my friend. Yeah, good for your US dollar, right? I like it. Definitely I like it. But why are you still here? Suspicious. Anyway, so because of that, right? And Jesus, all of this was a huge tangent, only to describe that what is the immutability actually want. What does it mean, immutability in the context of software engineer, which is in the daily activities. Immutability with things that is something that it won't change. It's like, hey, immutable, stay there. But in the context of computer science, if a program can change, I think that is not useful. There is no reason for that to exist. So what happened here is that the idea of immutability in the context of software is that we need to have the ability to, when change, we need to have the ability that needed change. We need to have the ability that needed change. The needed change needs to occur with intent. How can we control change? How do we control mutations? So that's a very interesting discussion.
And I said there's two different kinds of immutability that we want to pay attention to. So the first of those is assignment.
Okay. So according to Kyle Simpson, there are two types of immutability that we care about. Interesting.
Mutation. How do we control change? And I said there's two different kinds of immutability that we want to pay attention.
Okay. So there are two types of immutability that we pay attention.
So the first of those is assignment immutability.
Pay attention to. So we got is assignment, immutability. Okay, that's one.
Assignment immutability is the idea that when you assign something to a variable or to a property, that it is no longer allowed to be reassigned to some other value.
Exactly. Which is when you assign a value to a variable, you cannot.
The idea that when you assign something to a variable or to a property,
when you assign something to a variable or to a property, you can change
that it is no longer allowed to be reassigned to some other value.
Or property that is not able to reassign to other
is the idea that when you assign something to a variable or to a property, that it is no longer allowed to be reassigned to some other value.
Exactly. So it's not able to reassign to other value. So this is assignment immutability, right? And there are two types of immutability that we need to pay off, right? So is this.
And this is often, a big deal is often made of this. In fact, you'll know we talked earlier in the course about the const keyword. This idea that if I create a variable that can't be reassigned to, that I've somehow prevented myself from having bugs. So let's dig into that. Let's talk about assignment immutability. If I declare base price, as we are on line 1, with a var declaration, reassignment. With a var declared, or even a let, if you choose to reassign it to a different value later, which is a new value into base price. And the reason why that's important is that there are values which can be mutated. A number, for example, can't be mutated. You can't ever change 3.14 into anything other than 3.14. It just is that. Same thing with strings. You can't take the string hello world and modify one of the characters inside of that string. That isn't a thing that you can do. Those values are sort of inherently immutable. They are primitive values that can't really be changed. So we're not changing the value, we're reassigning the value in base price. We're creating a new value from an operation and assigning it into base price. And when we try to do the same thing on line 10, we get an error saying, no, that's not allowed for you to reassign. That's
exactly.
what the error means. You can't assign to a const variable.
But for
other than at the first time. And by the way, just a little note on const, this is sometimes overlooked. You cannot declare a const without assigning it a value. So you can
So for example, the const keyword, right? So for primitive values, that works well. Okay, that works. That's understandable. That's easy to get. That's easy to grasp on. Okay, that's easy to grasp on. Okay, that's easy to grasp on. Okay, and we can declare a const without any value. The idea here is to prevent the time sum death.
You can't say like const shipping cost, undefined in this two-state situation. Matter of fact, if you've heard, you may have read a blog post about something, it's called the temporal dead zone, TD.
To prevent the temporal dead zone. Temporal dead zone, which is what happened between the temporal dead zone. What happened when you declare a variable and then down the line you assign a value? What happened there? You know, it's like. So the idea here is to prevent this kind of
easy.
bugs.
And temporal dead zone is all about preventing us from seeing a const ever be in this weird in-between or this gray area state where it was undefined and now it's been defined to a variable. So that we've taken great pains to ensure that you have to assign it that value and then you can't reassign it later. Now, I've heard many explanations for why we should use a const in our programs. And as a matter of fact, some of the most vehement support for the const keyword comes from the functional programming community that does JavaScript programming. They feel like this is a big boon, it's a big improvement to the language to have a const keyword. I'm not convinced that it really does provide the value that it assumes to provide. And I want to dig into why I'm not really convinced about that. So if we think about this code, there's another way of avoiding this problem of assignment or reassignment. And this is actually how functional programmers prefer to work. If you think about the argument that a functional programmer makes, which says, I don't want my variable to get reassigned accidentally, so I always declare everything with const. That's the typical line. That's the typical statement. But then they don't actually assign many variables anyway. most of the time, I mean, this is called functional
Exactly.
programming for a reason, because most of the
don't
time,
assign
we're not
to the
doing
value.
assignment statements. Most of the time, values are being passed to functions and coming back from other functions. So if you see what's happening here, I can compute the new base price or the new shipping cost by simply passing the existing value to a function, computing it, and having that return value come back. And I can or cannot decide to assign that value to some variable. But those are separate questions. The computation of a new value versus the assignment to another variable, they're separate questions. And as a matter of fact, most functional programmers tell you, try to avoid assignment at all costs. You'll see long strings of composition where a function goes to another function and then it goes here and here and here and here and here, because heaven forbid we assign it to a variable temporarily and then use that variable later. We want to avoid that at all costs. So one of the questions that comes up in my mind when I hear a functional programmer say, no, const, you should absolutely only use const, is, do you really even care that much about const? You don't even like to do assignments if you're a functional programmer. So that's one of the reasons why I sort of suspect of, or I'm sort of in doubt of whether or not it's really bringing that much benefit to the table.
That's interesting. That's interesting. The suspicious here with const is that functional programmers where they don't like to assign variables because to generate a new state or because instead of mutating an object, instead of mutating a variable, you create a new function that return that new state. Okay, so far so good. It's quite understandable. Totally. Yep. Exactly. The suspicion. Yeah, the suspicion here with const is that functional programmers, functional programmers don't like to assign variables because instead of mutating a variable, you create a new function that returns a new state. Right? So far so good.
Here's another reason why I'm kind of concerned about the proliferation of const within our language. There is a lot of baggage that comes with the const keyword. Certainly this is not a new invention for the JavaScript language. Const was added to languages decades ago. And if you look even on a site like Stack Overflow and do a search for questions about the const keyword, you can find thousands and thousands of questions and problems that people have had with this keyword in basically every language that it's ever been added to. And I think one of the root reasons, if I'm trying to approach that question as an educator, as somebody who tries to understand what problems people who are learning things have and what they need to do to get over those problems, when I look at it from that lens, I think the real problem comes down to the English language being difficult to parse alongside of programming language. When we say the word constant, a lot of us mean something that doesn't change. When we say that in sort of everyday language, if we said the temperature has been constant today, it hasn't changed. today. That's what we mean. So we're implying something that doesn't change, and that's this gray area. What thing is it that's not changing with a constant? So if I point const at a value, if I point a const declaration at a value that itself cannot change, like 6.5, that's sort of a moot point. The value can't change anyway, so it doesn't matter. But if I point it at a thing that can change, for example, an array, now all of a sudden we see that there is a nuance difference that is really important. It's nuanced, but actually it should be the whole thing. Because the question is whether or not we care about reassigning a variable, or whether we care about a value that could be mutated having been changed. For example, adding or removing an element from an array, or reassigning one of the properties of an object, those are mutations to a value that are possible with certain value types, like arrays and objects, which basically aren't possible with a number or a string. So when we use a const with something primitive that isn't already changeable, it's not such a big deal. The nuance doesn't present itself. But when you start, for example, assigning functions to const, like we're doing here on line 3, functions are actually objects, and they can have properties on them. That isn't typically done that much, but you can use a function as an object, and of course that means the value.
Yes, because after all, we are not only are capable to assign is primitive, but also we do ask for functions. And functions, after all, they are first-class citizens, which is they are a special type of objects. They can be called, and they can be now as an object, add some property and change that. So this is the
you can be mutated. And even worse, when you use const with real objects or with real arrays, you create this confusion, I think, in people where they think in their mind initially that is a value that isn't going to change, when actually what the const keyword is saying.
Here is the assignment here. That's one of the problems here, especially when you're working with const. It's like you think that the values here, they won't change. No. It's the assignment to this variable that should not change. Let me actually do some exercise here, right? So if we, for example, go here and we say, hey, let's go to inspect this, right? Yeah, wartime body. If we say, hey, I want you now is to make all of the values inside of the array to be const, right? So for example, you say, hey, let's going to have, this is now users, Jesus. And then you have one user, 2, 3, 4, 5, a list of users. And then you say, hey, I want you to now is, well, change the value of the position 1, okay, to say, well, it's now 0. You might argue that you shouldn't do that, but the reality is that you can. And why is this? Because it's the conception, it's the concept, it's the idea behind that concept. It says, hey, this is the way of how you can now is make the immutability. Okay, give me a second here. All right, it's now the language is saying, hey, we in fact, all right, so we in fact is telling you to make is the assignment immutable. And this is quite, this is something that quite confuses a lot of people here, is that constant of this identifier of this value, of this variable, is not upon their value. Suppose there is assignment, and here we say, so then what in the F you mention this as a const, and why you don't put that with something other, with other reference with it? Why we don't use is another keyword?
Is it's an assignment that isn't going to change. So if I create an array and I assign it with a const.
So now if I create an array, in this case user, and then assign this, okay, and then assign to another primitive, it won't allow me to do that. And it won't allow me to do that at runtime, which is great. Okay. Sometimes good, sometimes not. But the thing here is, even though if I reassign with another array, let's say 1, 2, 3, 4, 5, 6, it shouldn't allow me to do that as well. Because at the end of the day, is the immutability here of the assignment, not the value. And most of the time, we as developers, through our experience,
declaration, and then later that value changes, the most likely outcome is that the reader is going to be confused. Certainly you can learn to get along with the const keyword. Certainly you can learn that keyword, you can learn its mechanics, you can use it so often that that becomes not a problem for you. But the default reaction for programmers seems to be to get it confused, which is why there's so many questions on Stack Overflow about it. People saying, well, I declared it with a constant and it changed, or it wasn't declared with a constant, it didn't change. I mean, it just creates perpetual confusion. So much so that some programming language communities had so much trouble with it that the language itself, namely I'm talking about Java here, they basically deprecated the const keyword and introduced a new keyword in its place called final. Because const had this English language baggage attached to it that said it's a constant, it's a thing that's not going to change. And now we're saying final sort of implies it's the final assignment of this variable. I guess that's helped the Java community. I'm certainly not a Java programmer, but they had to make that change because people were confused by it.
A very fun topic here. So, since const, okay, since const, can lead to confusion in terms of what is the immutability in terms of what is the immutability that we are what is the immutability what is the immutability that is using assignment only, which in other programming languages like Java, the community define a keyword called final. Damn, bro. The community say, you know what? Yeah, final, bro. Final. Final. That's interesting. That's very, very interesting.
And I've set up this entire course in the context of we want to communicate better with our code. Why would we use a feature which has long historical precedent for confusing people? So that's where the real trouble that I have comes from. It starts out already in the negative, if you will. And with any programming language feature, with any framework feature, the question that needs to be asked is, does that thing carry its own weight? Does it have enough benefit to overcome any potential downsides that it may present? Most of the time, I think we'd say that would be true. But with the const keyword, my claim is it doesn't really carry its own weight. If it's going to trip people up, if it's likely to, especially the new readers of a piece of code or people that aren't yet familiar with it, if it's going to have that strong potential.
This kind of confusion only trips people up. Yeah. So this kind of confusion is just only going to keep people tripping up. I love that, because esta clase de confusión lo único que va a hacer que la gente falopee mal. Se quede pegada. Oh man, and I passed through that, not only in terms of software, but also in terms of life. It's like, you do something, but you act differently. What is this, man? It's like, this is life. Welcome.
Trip people up. That strong, decades-long precedent for tripping people up. Then it ought to provide a really substantial benefit to our program to justify its inclusion. And the claims of its benefit are, I think, at best weak. So for example, in this slide, we see a const declaration on line 2, another const declaration on line 3. And then, of course, line 8, since it's named that way, it sort of implies it's doing a side effect. It's writing to a database or changing a record in the DOM or who knows what it's doing. But the point that I'm making is that this is a relatively short block of code. It's only 7 lines of code inside of the curly brace blocks. We're told many times that we should keep our blocks short, that we shouldn't be writing hundreds or thousands of line-long blocks because it's hard for the reader to understand things. My own personal kind of a style guide, if you will, or what I try to keep, is I try to keep no block, no function larger than what I can see on the screen at any given time. And at my general zoom level, that's about 20, maybe 25 lines at most. So if it's longer than that, I'm immediately thinking to myself, I should be refactoring this thing. I should be trying to break it down into 10, 15, 20 line at most. I shouldn't be having 100 line long blocks. And I'll be honest with you, you can see a lot of my code if you go to my GitHub that breaks that rule. So I'm not always perfect. In fact, I'm often not perfect at that. But it's a general guide for myself that I don't want to have these long blocks that are hard to read. So if you're following that sort of thing, if you're following what the general best practice is to have a short block, we need to understand that the idea of assignment is inherently related to the idea of lexical scope. The idea of assigning to a variable is inextricably linked to the idea that that variable belongs to a particular scope. When we do const shipping cost on line 2, we have created a variable that exists only for the next 6 lines of code. It does not exist anywhere else in the program. And that means that nowhere else in the program could possibly reassign it. We have a short block of code, and we have only a few lines of code that could possibly do the reassignment. So the typical argument is, oh, well, const signals intent. It tells the developer that's reading your code, you don't have to worry, it won't get reassigned later in the code. But if we're following best practice, that's not very many lines of code that it's asserting anything about anyway. It's not as if we have tens of thousands of lines of code that we couldn't possibly as a human juggle. Right here we have 6 other lines. And there's another way to say to the reader of your code, I'm not going to reassign a thing, and it's to simply just not reassign it.
Exactly.
As a matter of fact, if you're doing functional programming, don't assign at all. As little as possible, do assignments. So I'm not sure that the const keyword is actually providing all that much benefit, even in this best case scenario where you're saying to the developer, hey, listen, I'm not going to reassign it, because most of the lines that it could be reassigned are already clearly visible to you. And you can see that it's not being reassigned. In these particular cases, since we're inside of a block, my preference is to use the let keyword. And I use the var keyword at the function level scope rather than the let, because it says to readers, and has for 23 years, this variable belongs to the entire function. So maybe assignment immutability isn't such a big deal. Maybe it isn't the problem that we really ought to be concerning ourselves with. But there is a much bigger deal that I think we should be concerning ourselves with. That's the question of value immutability.
So which is value immutability. Okay. So since functional programmers, after all, they don't use assignment the value proposition of const for so the value proposition of const for assignment immutability is not a strong case here. But what we really care most of the time is value immutability.
Because unlike assignments, which are lexically scoped by their literal definition, they are lexically scoped to generally a small portion of our program. Values, especially values that are passed by reference, are completely portable. They can go anywhere in the program and even beyond the program.
So unlike assignment, that they can only exist in a functional scope or a function.
Values, assignments, which are
Exactly. They are, which you like assignment, they can only exist in a lexical scope. Whether it is a block, whether it is a function, lexical scope.
lexically scoped by their literal definition. They are lexically scoped to generally a small portion of our program. Value.
Block, function, model, small portion of the program. So now values, okay, are portable. They can live. Exactly, especially if you pass that as reference. Especially if you pass that, okay, values are portable, especially if you pass that by reference. Oh my God, yeah, it is.
Values, especially values that are passed by reference, are completely portable. They can go anywhere in the program and even beyond the program to other third-party code that is included in running.
By reference, they can be passed by the program and even third-party libraries. Damn, so it's like it's having.
So if you take an array that has some numbers in it and you pass it somewhere else, you have to be asking yourself the question, what is going to happen to that value? Value immutability is a much more important question. If we were trying to come up with some sort of rating system here, I'd say 99% of the problems that we face come from a value being mutated in a way that we didn't expect. There's some global state object that has 1,500 properties on it, and somewhere some weird obscure piece of code changed 2 or 3 of those properties in a way that we didn't expect. That's a value mutation and has absolutely nothing to do with whether you use the const keyword or not.
Exactly.
So value immutability is the big problem. 99% of the problem comes from value immutability, or value mutability, rather, and only 1% of the time at best does it ever come from reassignment. As a matter of fact, and I'm being completely honest with you, as a matter of fact, based upon my own sort of introspection about my processes and code, never once, not a single time, has there ever been a case where one of the bugs that I was trying to fix was, oops, I reassigned a thing that I wasn't planning to assign. That's never once been the problem that I've had. And I'm not saying that that's never been a problem for anybody. I'm sure that const exists because somebody somewhere reassigned a thing. But in 25 years of programming experience across a variety of languages, I've written, I can't even count how many bugs. I'm way better than all of you at writing bugs. I'm good at it. And all the bugs that I've written across a variety of languages, I've written, I can't even count how many bugs. I'm way better than all of you at writing bugs. I'm
way better than all of you at writing bugs.
Good at it. And all the bugs that I've written, never once has the problem been, oops, I meant to leave X alone. And instead I should have written Y or something. That just isn't generally the problem that I face. And so I'm skeptical as to whether or not that assignment problem is really so widespread. And I think we're not getting the proper attention on the value mutability problem. Did you have a question?
I was just saying the only example I've ever seen is like doing a for loop and accidentally reassigning I when you use two for loops or whatever.
That's a great point, right? So like, yes, you could definitely accidentally have a variable updated inside of a for loop and then it throws the for loop off. Some people do that on purpose. They'll like write for loops where they skip or go back, and I've written code like that before, and that's always been a pain in the neck to manage and debug later. It's always been a terrible idea. But I'm glad you bring up this point because that's an example where it theoretically could be a problem, and guess what? Const doesn't solve that problem for us because you, by definition, have to update that incrementer in your for loop. So you can't declare it with a const anyway. So yes, it's a problem, but it's not a problem that the const keyword is solving for us. Let's take a look at some examples of value mutability and how we can address.
So value mutability. Oh my God.
This question of value mutability. So here I'm creating an order details object, and I'm conditionally adding some stuff in. So I need for this thing to be able to be mutated because I need to run some other conditions and maybe update some properties or things like I am doing on line 7 through 9. And then line 11, I pass that object, and because it's an object that's passed by reference, I pass that object by reference into this process order function. Now, do any of us have any idea what process order is doing? Well, we don't see it here. It's not local, so the answer is no. We don't know what process order is doing. Can we go and look at all the code in process order and figure out? Sure. But if there was something in this block after process order that was relying upon order details, we now automatically would have to have the suspicion, if we're paying attention, we have to have the suspicion, did something change about the order details object? And if that isn't our intuition to ask, then it is almost certainly going to be the source of a bug at some point.
It's certainly a bug.
One of the things that we do as functional programmers is try to predict where the bugs are going to be and avoid them before they occur by using patterns where they can't happen. And passing a value by reference where somebody could accidentally or intentionally change a thing in a way that we're not expecting is like putting up a giant neon sign that says, please create a bug here that I haven't planned for. And this is why functional programmers take this so seriously. This is why immutability is one of the most critical topics, and I think often undercovered topics in all of functional programming. Because values get passed everywhere. We pass arrays and objects and functions all over the place. And we should be asking ourselves every time we pass it, how do I know that that isn't going to change in a way that is going to create a bug in my program? When I pass the number 42 or the string hello world, I'm not worried because I know the language already protects me. But when I pass an object in an array, I don't have that same level of guarantee. So even without going and looking at the process order function, I'm going to make an assertion that the reader of this code could benefit from some sort of process or convention that would allow them to know that they can trust that order details is not going to get changed. So what do we need?
So the value immutability here, okay? So value immutability is value immutability is that the problem is that the problem of mutating a data is that it can the problem of mutating data is that we need to carefully program. So the problem of mutating the data is that we need to carefully do that to prevent side effects. Oh shit. So the problem of mutating data is that we need to carefully do that to prevent side effects. Okay? So functional, exactly. Side effects. So functional programmers, something that he mentioned. Functional programmers, okay, because you bring your expertise from another field.
Value immutability is a much more important anyway. So here I'm creating an ordered sequence. I pass that object by with something in this blockchain. Going to be the source of seeing patterns where they can't thing in a way. That's why functional programmers take this so seriously. This is why immutability is one of the most critical topics, and I think often undercovered topics in all of functional programming. Because values get passed everywhere. We pass arrays and objects and functions all over the place.
Exactly. So the problem with mutating data is that we need to carefully do that to prevent side effect. Because values are passed everywhere and are shared, exactly, passed. So values are passed everywhere. So values is like the air. So values is like a fly. Okay? It can get in any place. Get in, get out, you know. It's like the wind. Get in and get out in any places, right? So values are passed everywhere. So functional programmers.
And we should be asking ourselves every time we pass it, how do I know that that isn't going to change in a way that is going to create a bug in my program?
Mm-hmm. We need to ask. So anytime we pass down
objects
data,
and functions all over the place. And we should be asking ourselves every time we pass it, how do I know that that isn't going to change in a way that is going to create a bug in my program?
Mm-hmm. So anytime we pass down data, ask yourself, how do we go? So ask yourself, how can we guarantee that when I do that, it doesn't create that?
Objects and functions all over the place. And we should be asking ourselves every time we pass it, how do I know that that isn't going to change in a way that is going to create a bug in my...
Mm-hmm. Yeah. How is it going to change? Anytime we pass on data, ask yourself how that isn't going to change.
Arrays and objects and functions all over the place. And we should be asking ourselves every time we pass it, how do I know that that isn't going to change in a way...
Mm-hmm. How do I know? How do I know that how do I know that how do I know that that data isn't gonna change in a way that is going to produce a bug?
That is going to create a bug in my program. When I pass the number 42 or the string hello world, I'm not worried because I know the language already protects me. But when I pass an object in an array, I don't have that same level of guarantee. So even without going and looking at the process order function, I'm going to make an assertion that the reader of this code could benefit from some sort of process or convention that would allow them to know that they can trust that order details is not going to get changed. So what do we need? Your instinct might be to say, because we're talking about immutability, aha, we need an immutable data structure. No, we don't. Value immutability is a much state that incrementer, is the for loop off.
Accidentally.
Problem. Somebody somewhere reassigned was trying to fix was introspection about my or value mutability. Right, buddy? Oops. Problem is that before and solve that problem for us because you on keyword is solving address adding some stuff past. Well, we don't see it here. It's not something in this block after process order that was relying upon order details. We now automatically would have to have the suspicion, if we're paying attention, we have to have the suspicion, did something change about the order details object? And if that isn't our intuition to ask, then it is almost certainly going to be the source of a bug at some point. One of the things that we do as functional programmers is try to predict where the bugs are going to be and avoid them before they occur by using patterns where they can't happen.
Because it's a particular approach. Okay. Is it not? Yeah, exactly. You're tending your own work. We are tending our own work. Here with this. No, okay. So, functional programmers.
One of the things that we do as functional programmers is try to predict where the bugs are going to...
Exactly, this is one of the things. So one of the things that is try to predict with the use of mathematics. One of the things that functional programmers does is to try to predict where the bugs are going to be, where the bugs are gonna be. So one of the things that functional programming does is to try to predict where the bugs are gonna be by introducing patterns that allow to do this.
Going to be and avoid them before they occur by using.
Exactly. So try to predict where the bugs are gonna be. One of the things that functional programming does is to try to predict where the bugs are gonna be, avoid them, by introducing patterns, or by using patterns where they can happen. By using patterns where they can happen. And some of those patterns here is immutability. Immutability data structure.
Patterns where they can't happen. and passing a value by reference where somebody could accidentally or intentionally change a thing in a way that we're not expecting is like putting up a giant neon sign that says, please create a bug here that I haven't planned for. And this is why functional programmers take this so seriously. This is why immutability is one of the most critical topics, and I think often undercovered topics in all of functional programming. Because values get passed everywhere. We pass arrays and objects and functions all over the place. And we should be asking ourselves every time we pass it, how do I know that that isn't going to change in a way that is going to create a bug in my program? When I pass the number 42 or the string hello world, I'm not worried because I know the language already protects me. But when I pass an object in an array, I don't have that same level of guarantee. So even without going and looking at the process order function, I'm going to make an assertion that the reader of this code could benefit from some sort of process or convention that would allow them to know that they can trust that order details is not going to get changed. So what do we need?
So one of the patterns, one of those patterns is to make data read only, or to make value read only, immutable data structure.
Your instinct might be to say, because we're talking about immutability, aha, we need an immutable data structure. No, we don't. Because what we need right now is we just need to say that this value is read-only. And that is a different sort of a claim than asking for it to be an immutable data structure. And I know that seems counterintuitive, but hang with me because we're going to talk about what immutable data structures are about. And I'm going to say, right now we're focused only on the claim, could I say that this thing is read-only? That it cannot be mutated in any way. Because I think a lot of times when people think, oh, I guess I need an immutable data structure, actually what they need is just a read-only data structure. A data structure that can be read but cannot be written to. And those are different than immutable data structures. So it turns out, it's built into the language, there is a way to have a read-only data structure, pretty simple, and that is to call object.freeze. Object.freeze, as you see on line 11, is telling that object, you should change all of your properties to have the read-only attribute on them so that none of them can be changed. The object can't have properties added, it can't have properties deleted. It is, however, only shallow. So be aware that if you had nested objects of nested objects of nested objects of arrays, you would have to freeze each one of those levels to get that same level of guarantee. But in our simple case where we have a simple single-layer object, a simple call to object.freeze gives us the guarantee. But I'm actually going to make a slightly even different claim. I literally don't care if object.freeze actually does what it's supposed to do. I mean, it could be like an empty hollow polyfill. The real point is that I am communicating something to the reader of the code at this point. It is less important to me that it actually be read-only, and more important to me that the reader be able to know I'm saying you don't have to worry about this thing changing.
The important thing here is to communicate the intent of the programmer about this value. About this value. So for example, here is like, hey, this data that we're passing down is like, hey, this data that we're passing down cannot be changed, or in other words, is read only. So the order detailed data that we are passing is only is read only.
As a matter of fact, it'd be nice if the language gave us some sort of syntactic facility for that. Maybe an operator when we make an object or when we pass it or something. They're not ever going to probably add something like this, but it's a harebrained idea. But it'd be nice if there was even a lighter weight way than saying object.freeze. But basically what I want is an annotation that tells the reader, you don't have to worry, it's not going to be modified. It's read-only.
Mm-hmm. The other data that we're passing is read-only. Don't worry, it's not going to be modified.
You don't have to worry about it being mutated in some way that you don't expect. Now, the good part is that object freeze does actually do what it's supposed to do. So it gives us not only the signal to it, but it enforces it from a runtime perspective. That if process order were to try to do something that it shouldn't, the whole program's going to blow up and an exception is going to be thrown. Now, the reason why I say I don't actually care about that part is because it is vanishingly rare that something like that, like trying to reassign to a property that was actually set as read-only, it's rare that that's been wrapped in some try-catch and gracefully surfaced to the user as a, oops, something went wrong. Because if that occurs, if you pass in a read-only data structure to process order, and process order is in the habit of wanting to mutate the thing, then you have a fatal, unrecoverable bug in your program. It's the kind of thing that we'd like a linter to catch for us. And maybe depending on what kind of, programming language, or if you're using a TypeScript or something like that, maybe you can get a linter, a static checker, to sort of tell you about that problem. But if it passed in as a read-only and then process order tried to catch it, that's going to create a fatal error condition, and you, the developer, are going to fix it. What I'm really concerned about is when we don't have those fatal errors, but we have those subtle, crappy bugs that are really, really hard to debug. The user's still able to check out, but it charged them $1 extra on the order than it should have, and nobody can figure out where that extra $1 came from. Those are the terrible bugs, aren't they? They're the ones where there wasn't a fatal crash, but it was still a bug, and it's really hard to reproduce the conditions for that. And one of the ways that we avoid those sorts of things is by telling the reader of this code, or at least, whether we avoid the bug or not, at least make it easier to diagnose, is we tell the reader, you don't have to worry, the object didn't change at this point. It's not going to change.
Exactly.
So read-only data structures are data structures that never need to be mutated.
Mm-hmm.
That's key. A read-only data structure is a data structure that never needs to be mutated ever again. You might create it and do some mutation in its creation process, but at some point you freeze it, you say it's done, it's final, it's complete, and then you move on. You use that in that final value form for the rest of the program. That actually there's a lot of those. There's a lot of times when we create a config object that we're going to pass in to an AJAX call or something like that. That's an object that isn't going to change, or at least it shouldn't, otherwise.
Mm-hmm. So for example, exactly. So examples of read-only data structures are configuration. Usually they don't, configuration. Usually they don't change. Or they change.
We're probably going to have bugs that we don't expect.
Slowly.
So that's an example. When we pass in an object and you pass in a configuration array or something like that, you even take a JSON response from an API. That's a value that's done. It's come back from the database. It's come back from the API. It's done. It ought to be marked as read-only, because there's no reason for us to be mucking with that in some way that's going to end up creating a misexpectation and therefore a bug somewhere else in the code. Those are all data structures that don't need to be mutated. But that certainly can't be all of our data structures.
Exactly.
We certainly...
API response, However, sometimes we need data to be mutated or to generate a new state.
I can't imagine a program that would do anything useful if all of our data structures were in this read-only state. Some of them, sure, but all of them in a read-only state would mean a program that was fixed and did nothing, and we could just delete it and move on.
Exactly. So sometimes we need data to be mutated or generate a new state. Otherwise, if all states in our program are read only, it's just a fixed program that we use and delete.
So when I take that process order function and I pass in an order to it, you'll notice here that I'm trying to change it because I'm doing something that makes sense only for the database. I'm not even thinking about what somebody might have done with that order object after having called me. I'm just trying to make sure there's a particular flag on it before I try to save it to the database. You see the mutation there? The mutation that occurs by reference is, by definition, a side effect. We have an impure function. Of course, we have an impure function because of the database call, but we have another impurity which can create huge bugs in our program. So just because somebody may or may not remember to pass in object.freeze, I have an even more important point to make about this idea of value mutability, which is if somebody passes you a value that is in its identity mutable, something like an array or an object, then it is incumbent upon you, the author of the function. You don't know all of the call sites for this function. You don't know whether they're going to pass object.freeze or not. The best thing for you to do is to always assume that it's a read-only data structure. Always assume that you're not allowed to mutate it. Don't assume that because you mutate it and you don't see an error at that point, that nobody else is going to try to pass in an object.freeze data structure, in which case you would have a fatal failure. Always assume that you're not allowed to do line 3, you're not allowed to mutate it. So what do? We need to add a status field to it before we save it to the database. The answer is, you make a copy of the object. You make a copy of the We need to add a status field to it before we save it to the database. The answer is,
so in a function, once we receive a data, instead of mutating that, like the next image, or like the image below, which is here, you got it, calendar, exactly, calendar, calculate what it is on the finder. Finder, which is here. Okay, just finder. Where are all this image, bro? Desktop, screen recording. Is this one? There you are. Okay. Instead, but again, this is the particularly patterns that functional programmers, one of the things that they do is to try to predict what errors, try to predict when a bug happens, avoiding by applying some of these patterns. By applying or by using patterns where they can happen. this is a pattern that allows, this is a pattern to prevent that this happen, to prevent that bugs happen. So instead of that, we use is this particularly, this particularly pattern from the functional programmers as a way to prevent ourselves, as a way to prevent, as a way to prevent bugs in our code, as a way to prevent bugs in our code by mutating the data. So in this case, we use this particular pattern from the functional programmers as a way to prevent bugs in our codes by mutating the data, which is, hey, you know what? Always return is a new state.
You make a copy of the object. You make a copy of the object, which is what I'm doing on line 2. And that copy, I'm simply using the ... operator, that's object spread. You make a copy of that object, and then you can mutate it internally all that you want, because you're not having a side effect on the outside program. You should always, always assume that it's a read-only data structure, no matter what. So there's two sides of this issue, and don't lose track of them. One side of the issue is that when you call a function and you're going to pass in a data structure, do your reader the benefit of annotating it that you want it to not be changed. Use something like object.freeze. And secondly, and maybe even more importantly, when you write a function that receives data structures, treat it as if it's read-only no matter what. Do your reader the benefit of annotating it that you want it to not be changed. Use something like object.freeze. Pass or what? So there's two sides of this issue, and don't lose track of them. One side of the issue is that when you call a function and you're going to pass in a data structure, do your reader the benefit. Two sides of this issue, and don't lose track of them. One side of the issue is that when you call a function and you're going to pass in a data structure, do your reader the benefit of annotating it that you want it to not be changed.
So some of the practice here to prevent or to try to prevent bugs in your programs, some of the practice here to try to prevent bugs in your programs from the functional programming is to one, when using, okay, interesting. So when using or when defining, when passing a data structure, interesting. When passing a data structure, okay, again, this is part of the functional program. So when passing a data structure, okay, so when passing a data structure here, so when passing a data structure to a function, use the annotation if needed. If needed. Use the annotation. Use the annotation that indicate the user. Use the annotation that indicate the programmer or the reader of your code that you want to pass a read-only value with object.freeze. And the other is assume exactly when writing exactly. So write a function, okay. So pass a data structure to a function. Exactly. Pass data structure. Pass a data structure to a function. Use the annotation. Pass that structure to a function. When passing, you can say is passing data structure to a function. Use the annotation to indicate the reader of your code that you want to pass the read-only value with the object.freeze. Good. One. The other is that writing a function assume. So writing a function is, so yeah, writing a function, create a new copy of the data to work on.
Use something like object.freeze. And secondly, and maybe even more importantly, when you write a function that receives data structures, treat it as if it's read-only no matter what.
Mm-hmm. So writing a function, treat the data that you receive it as read-only by creating a copy of that. By creating a copy of that. Mm-hmm.
Make a copy of it, make your changes to your local copy. That's how we deal effectively with value mutability. But again, that still only tells us something about data structures that never need to change. What do we do with data structures that do need to change? Well, you can't treat all data structures as immutable data structures, as read-only data structures. Some of them are going to have to be mutable. And here's the real counterintuitive thing. When you have the need for a mutable data structure, that is one that is not read-only, what you actually need is an immutable data structure. Let me say that again because it's really strange. When you need a mutable data structure, what you actually need is an immutable data structure. So what am I talking about here? What do I mean by that? An immutable data structure is one that allows not no mutation, but rather structured mutation.
Practice.
Structured, controlled, intentional mutation, as opposed to just willy-nilly make an
practice.
assignment statement and create a side effect somewhere. It's the next level from a read-only. You should start by asking, is this ever going to need to mutate in any way, shape, or form? If so, then I don't use a read-only. I need to do something immutable. But if it never needs to change, then just stick with the plain, simple read-only data structure. We only step up to this immutable data structure if it needs to mutate. So what exactly is an immutable data structure? It is a representation of the data structures that we are used to dealing with. We're used to dealing with data structures like arrays, where we can access things at index positions. We're used to dealing with things like objects, where we can access things at named property positions. It's things like that. It's data structures like that. But where you don't have access to the actual underlying data structure, what you have only is an API to access it. And the API creates a layer of control that prevents unexpected changes to the data structure. Specifically, what an immutable data structure says is unless you switch it into a special mode that allows this. So by default, it's not. If you switch it into a special mode, you can literally go in and muck with it if you have like a performance problem that you need to deal with. But in the general state, an immutable data structure says, essentially, you cannot change the data structure. You can only create a new data structure with the change having been applied. Similar to what we did a couple with it if you have like a performance problem that you need to deal with. But in the general state, An immutable data structure says, essentially, you cannot change the data structure. You can only create a new data structure with the change having been applied. Similar to what we did a couple of slides ago when I made a copy to the thing and then I added the status field to it. It's similar to that concept. It says, listen, I need to add something to it, and the response from the API is, okay, but here's a new data structure with the change applied. I'm not going to let you modify the previous one. And the reason I'm not going to let you modify the previous one is that somebody else in the program might be relying upon the previous state of that object. They have to opt in to saying, I want your version of the object. You don't get to decide, process order, that you're going to affect something at a distance somewhere else in the app. You could return the new order, the processed order with the status field, and allow the caller of your function to decide what they want to do with that information. But you don't get to mutate it from afar. That's what I mean by saying that an immutable data structure creates a control mechanism. It creates a controlled, intentional way for the mutation to occur. And by default, it simply says, let's make a whole new object. A whole new array, a whole new list, a whole new object, a whole new map, whatever the data structure is, make a whole new one of those with the change having been applied. Now, the question becomes, how could that possibly be performant? How could it possibly be performant for me to make a whole new copy of this array or a whole new copy of this object every single time I need to make a change? Because the kinds of objects and arrays that we're talking about that need to be mutated probably need to be mutated a lot. Not once or twice, not 3 or 10 times, but like thousands of times a second. So the ante is high for if I'm going to change this thing over and over and over and over again so often, and I'm creating all these new ones and throwing all the old ones away, at worst, I mean at best, I just have a bunch of garbage collection, but at worst you consider all the CPU churn of making all those copies over and over again. And this is where the real power of an immutable data structure comes in. Because the way immutable data structures are designed is designed specifically with this optimization in mind. In theory, in functional programming, we just say, no, you don't make a new thing, you don't make a change to a thing, you make a new thing with the change applied. But in practice, that means real cost, like garbage collection and CPU. And so it is the job of an immutable data structure to mitigate that real practical cost so that we get closer back to the theoretical benefit of what an immutable data structure is. So if you use an immutable data structure, what it's actually going to do is not create a whole new copy of the object when you try to change a property, but rather make a new object with the new information in it and internally have a pointer back to the previous one. It's actually a little bit like a Git repo, where every time you've committed something, you're just storing a diff compared to what it was before. An immutable data structure is essentially conceptually like a Git data structure, where each new object in the chain that you've created is just a diff on the previous object. It stores internally that there's now a new property or that a property's been changed or something like that. And so you're not paying nearly as much of the performance penalty CPU, and you're not paying the garbage collection penalty. In the general sense. There's certainly corner cases or something like that. And so you're not paying nearly as much of the performance penalty CPU, and you're not paying the garbage collection penalty. In the general sense. There's certainly corner cases here, and it's why immutable data structures can allow you to opt in, for a time period. You can sort of crack it open, make some changes, and then lock it back together. Those things have to exist because sometimes we have performance bottlenecks that we need to deal with. But in the general sense, we want to just use the data structure in that conceptual way and allow it to abstract away those performance optimizations for us. So, how do we get immutable data structures? We do not, at the present time, have immutable data structures natively in JavaScript. There have been a couple of rumblings from some people on TC39 that maybe someday that will happen. But you need to understand that when somebody says,
no, man, and this was what, when? 2018?
Somebody on TC39 has talked about maybe it happening. That means that we might get it a decade from now. That's not like, it's going to happen in a few weeks or a few months. The timelines that we're talking about here are, it's been talked about for the last 5 years, and now there's like a first proposal, and then 4 years later they've vetted, and now it's finally landing. So we're not talking about this sort of stuff landing natively in JavaScript anytime soon. But it's at least encouraging that some conversation has started about it. Some people in that realm have started to say, maybe this would be useful for JavaScript to have built in natively. And there would be a huge benefit to the language being able to highly optimize these sorts of things that we're talking about. In the interim, in any place where you have a data structure and it is important for you to manage the mutations to that data structure, you're going to need a library that provides you an immutable data structure. And there are a couple of major ones out there that you will hear about. Probably the most common of those is called Immutable.js. It comes from the folks at Facebook. So if you want to check out Immutable.js, they've got a bunch of great...
Okay, but that'll be all for this video. Yeah, take care. Bye-bye.